Hey everybody, it's Ripley back again, and we're going to talk about Stokes' theorem today. It's, it's going to be interesting, I promise you. This is Stokes' theorem, okay? So we already know about S, it's a surface. It's an oriented, piecewise, smooth surface, so we got to orient it some way. Positively oriented makes it easiest for us. We're talking about C, which is a simple, closed, piecewise, smooth curve that bounds S. And I'll show you what that means here in just a sec. I want to get into the mathematics first, and then so you have that sort of sitting there, a little bit of mathematical theory behind it, and then I'll show you what this means. This is not going to be a long video. This is the penultimate video of Calculus 3, vector and multivariable calculus. So I'm not going to crush your spirits. However, I do want to chat a little bit about this. So an F, last but not least, I interrupted myself, is a vector field whose components have continuous derivatives. So continuous partials is what they're saying. Stokes' theorem says that the line integral of f dr, now let's make sure that we understand what this f dr is. It is a boundary that bounds S. So it's a surface curve that goes around the surface of S, all right, of f dr. It's just the same line integral as we always had before, except we're very clearly defining what C, I can write on these. What C is, excuse me, same line integral, is equal to the double integral or the flux integral, but instead of f, it's of the curl of f. Remember, the curl of f is still a vector. So we're still taking a flux integral, it's just that the flux integral that we're taking has to do with curl. Now, let me explain what this really is. It's an extension of Green's. All right, if you recall, Green's, just real quick review, says that if I take the line integral of p dx plus q dy, that this is equal to the double integral over the domain, right? Remember, so what I've got is a two-dimensional vector field here. It lays in the plane of the partial of q with respect to x minus the partial of p with respect to y dA. Well, there's a problem. What do we do in the three-dimensional case? Because now what I've got, let's slap that sucker on. Now what I've got is I have a line integral of p dx, that's a d by the way, plus q dy plus r dz. Well, Green's only worked in 2 space. So what do we do in 3 space? Well, let's look at what the curl of f is, just really quickly. I know we've already done it. The curl of f is the grade crossed with f, right? We call that grad cross f. And remember how we got that. This is equal to, if I take the cross product, I, j, k, and then I take these partials with respect to x, this del with respect to y, del with respect to z. And this is by no means a rigorous proof. I get p, I get q, and I get r. What it does is it extends what we can do into 3 space. All right, so that said, now remember, this is an equal sign. We like equal signs because it can work either way. If I'm dealing with a really nasty line integral, but dealing with this curl of f dot ds, which we've dealt with flux integrals, is easier, then I can do it. Likewise, if I'm taking the surface integral, this flux integral of the curl of f dotted with ds, I can just pop over to f dr, right? To this, the line integral of f dr. Now, let's remember all of our techniques. So I know that if I want to take f dr, and I should, notice how they use bold, I'll use these little guys, right? Right here, there's lots of ways that I can do this. I can take the integral from a to b of f of r of t of r of t. These are all vectors. I'm trying to be good, you guys. Give me a break. Times r primed of t dt. That was one way. I can use Green's. That's another way, right? And now I have this way. I can take the surface integral of the curl of f dotted with ds, these guys, and I've got it. Now, like I said, if you think about taking this operator, right, this operator on a vector field, it smells a whole lot like Green's theorem, but Green's theorem that's been extended into 3-space. We'll go over the rigorous proof in a special case, and you can generalize it to any vector field. But we'll discuss that for a minute or two. We're just going to take a minute in class, okay? Now, that is the hand-waving sort of proof of why, if my vector field is in 3-space, right? If my vector field describes 3-space, then I get this curl as opposed to this. Now, if I wanted to write curl of f out as the actual curl of f, I could, and it would look a whole heck of a lot more like this, wouldn't it? Do you see what I'm saying? Okay, cool. I don't want to do that because you guys will want to punch me in the head. So that's kind of an overall, kind of a mathematical overview of why this is indeed true. But remember, let's be very clear. If we're in 2-space, if our vector field is on a plane, then we only care about Green's. But if it's in 3-space, right, if I'm dealing with this vector field, right, which is the same thing as that vector field, then I get to use Stokes's, or Stokes. I always screw that up. Stokes theorem. Okay, now I'm going to leave for a sec because I want to grab a picture and I'm going to drop it in and I want to talk about what's sort of really going on here. Well, I'll give you a couple of examples of what this really means, because we can't just hem and haw about what this is, because the use of this is really, really important, as is the use of, I guess when I draw that I imply that I've got a closed path. Same thing. This has to be a closed path for this to work. We have to understand that. All right, I'm going to give you some actual kind of real life examples of what this would sort of look like. Okay, I'll meet you back here in just a second. All right, so I'm going to give you a graphical explanation of Stokes' theorem because it seems a little crazy, but it's pretty easy. I'm going to do it in 2-space. Okay, and I'll generalize it to 3-space here in just a sec, but it'll be easy to see what it's easily generalizable. Let's put it, that's not a word, but you know what I mean. Okay, so we got the weirdest duck in the whole wide world, and this duck likes to swim around rivers or streams in rectangular patterns, all right? And he likes to positively orient himself as he goes around. Sorry for my gender bias, people. But so we've got a vector field, and this thing's cruising around. We already know that this path is going to be, if we take the line integral of f dotted with dr, then we know that's the work that the duck does, right? Now, let's think about what Stokes' says. It says that this is equal to the double integral over the surface of the curl of f dotted with ds, right? We know this is just a flux integral across the curl. So I'm going to do something. Now, again, we're in 2-space right now, so don't panic, but I'll do something with you guys here in just a sec. I'm going to cut this thing up, all right? I'm going to cut it up real simply. And I want you to think about this as the surface of the river, as it were. All right, so, and therefore it's the vector field, right? We know that the surface of the river is going to behave with vectors, and there's going to be all kinds of eddies and curl and divergence in all directions, but we're not going to worry about that. All right, so, but think about this. I'm going to take each one of these rectangles and I'm going to treat them kind of like a Riemann sum, right? Back in integral calculus when we first started playing with this, we weren't afraid of taking little rectangles and adding them up. If we take an infinite number of them, we get the exact area. If I take an infinite number of summing up all these curls, then I'll get the surface, I'll get the flux integral across this thing, or surface integral. Okay, so here we go. Watch. Let's assume, well, it doesn't really matter. We're going to just positively orient all the curl. All right, so this little quadrant right here has this curl. Now, this little quadrant, remember, our curl, our positive curl, is going to be, and even if it's negative, it doesn't really matter, but let's assume that all of the curl is positive. All right, but watch what happens. Now, this little quadrant is going to have positive curl like this. All right, now what do you notice right here? Oh, wait, those two cancel. Now, wait, let's do this guy. Okay. Here we go, and here we go, and here we go. Cancel again. Let's do this one. Here we go, here we go, here we go, here we go. You see what's happening? All of the curl on the interior is canceling. I do this one. Boom, 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 boom. Cancel, 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 cancel. Again, might as well finish it up. I'll do it quickly, though, so I don't annoy you guys. More. And boom, and then last but not least, Look at that. Isn't that cool? And the only thing that's left, all of this, badly drawn, sorry guys, I got a little bit of lag today. All of that canceled, and the only thing that is left is the exterior, which we know is the line integral. So these two are identically equal, all right? And that's what Stokes said. Now, I can generalize this to 3-space relatively easily. If I take this, and I'm going to do a little of that, right? Now think about this. If I've got this little bounded region, right, and I add up all the little swirls, well, these guys are going to cancel as they go, right? So all these little curls are going to cancel because over here everything's moving in a counterclockwise direction. So this and this will cancel. And the only thing that I'm left with, fabulously, and thank God, or it'd be a lot more difficult, is the outside of the surface, which says that the flux of the curl of f is exactly equal to the line integral. Now, this is a theorem. Like all theorems that contain inequality, it goes in both directions. It works like a hammer. You can use this thing however you want. If I want to use the double integral or the flux integral to make a nasty line integral with multiple piecewise parameterizations, I can do that. If I've got some god-awful monstrosity of a flux integral here, and you see simply that you can use the line integral, do the line integral. That's the beauty of it. But it's super elegant, it's super beautiful, and it's one of the coolest ramifications of vector calculus. All right, hope you enjoyed. Have a lovely day, and I hope this was helpful. See you tomorrow.